So yeah, as mentioned before, so I'm Nils Niggemann from Free University of Berlin, and I am talking about frustrated magnets, and in particular, these kinds of magnets which host these pinch point features, but not only the conventional ones that you are probably familiar with, but some new types of pinch points that have been studied in the past. And I will, in particular, also consider the effect of quantum fluctuations in these kinds of models. So just to briefly set the stage, I am looking at models which can be written as a Heisenberg model. So that means that the spins are coupled isotropically. And in particular, now, if you replace the spin operators by classical vectors, in some of these models, you will find that there's an extensive ground state degeneracy. And a very natural question to ask now is what happens if we include quantum fluctuations to this classical system? So if you replace these spin components here by Pauli matrices, you will get a quantum model, and then many things can happen. The degeneracy could split up and you have a ground state which is just dominated by this quantum selection, or you could have a number of more complicated states. So just to make clear which kinds of states we can have in such a model, we have the more boring types of ground states, such as a classical paramagnet, or I guess that is not a ground state, but at finite temperature, which is large, you will have just fluctuating spins, and below some temperature they can order, but you can also have more entangled kinds of states, such as a valence bond crystal, which doesn't break any spin rotation symmetry, but it breaks point group symmetries of the lattice. And finally, of course, there's the infamous quantum spin liquids that many people here have already talked to great detail about. And also at this point in this entanglement arrow here, I can place the phases of quantum spin ice and fractonic phases of matter, which will also be interesting in this part of the work. So yeah, just because I will be needing a lot of the concepts here, let me briefly re-summarize the main points about spin ice. So as you know, spin ice is most popularly studied on the pyrochlore lattice. So you have a number of corner-sharing tetrahedra, and this classical nearest neighbor Heisenberg model, you can then just write as a sum over all tetrahedra, where you sum the spins inside a single tetrahedra and you square everything, and that gives you back the original Heisenberg model. So what is nice about writing it this way is that you can immediately see that since this object here must always be positive, the ground state fulfills this very simple so-called ice rule that the sums over all spins inside a tetrahedra must sum up to 0. And the reason why this rule is also referred to as a Gauss rule, as a Gauss law, is that you can coarse grain everything, and you will actually get an emergent U1 field, very similar to electrodynamics. So often this field is called a magnetic field, but in this case, maybe it would be more apt to call it an emergent electric field. So you write this as a linear combination of spin operators, and you will, instead of this sum here, you will get a continuous divergence-free in the ground state emergent field. And in the case that there's defects, so you have excitations, for instance, by thermal fluctuations, you can have these magnetic monopoles which can fractionalize and travel throughout the lattice. Okay, so far nothing new. Maybe also another point is how to actually detect these kinds of states. So typically this ground state constraint, and now I've written the divergence-free version, so this is really the ground state now, comes with a susceptibility that has a singularity at specific points in K-space. So often is plotted the HHL plane, which is exactly this cut here where Qx equals Qy, and then you will see that at this point the susceptibility is non-analytic, because if you approach it from this direction, you will get a different limit than if you approach the pinch point along this direction. And you can also see that here, if you let Qx and Qy go to 0 across different directions. And just so you see it, this is how everything would look in 3 dimensions, because typically only you see this one. So as I mentioned before, a very natural question to ask yourself is to consider the effects of quantum fluctuations in these kinds of systems. And this has been done in the past, but not exactly not directly for Heisenberg models, which I've shown you before. but an easier version to approach this kind of problem is to start with Ising spins, where you can actually have this, this kind of ice rule constraint in an exact fashion. And you can then include quantum fluctuations by turning on the interaction Jx and Jy. So this is what you see here. And what people found is by treating these interactions perturbatively, you will still have this emergent U1 electrodynamics with very exciting photon excitations that have made this field of spin ice very big. So along this line, you have what is called a quantum spin ice. On the Heisenberg model, so if you would follow this line to this SU2 point, the question is a lot more complicated. So typically what you will see is that these bow ties that you've seen before, they are still visible, but they can be broadened by several effects, for instance, by finite temperature, but also by quantum fluctuations. And both of these are maybe not so surprising. Finite temperatures, of course, include these defects. So the ice rule is not fulfilled exactly and you won't get pinch points. Whereas for quantum fluctuations, you cannot just simply write down this ice rule because the spin operators do not commute, at least for non-Ising spins. So regarding the ground states, there has been a great number of numerical studies on this kind of model, and it's not completely clear yet what kind of ground state it has. But so far, the most recent numerics seem to point out that there's some kind of symmetry breaking. So not spin rotational symmetry breaking, but valence bond crystal ordering. So for the inversion or C3 symmetry is broken, or perhaps both of them at the same time. So maybe in the near future we will see more and more studies to verify which exactly is the case. So here's one of the proposed ground states by a paper of Nikita Astrakhansev that was proposed recently, and yeah, other kinds of proposals were similar to that. So how do we move on from here? And at this point, I want to just quickly introduce you to a very nice paper that was recently published by Owen Benton. And he generalized this kind of ice rule constraint by considering other types of lattices. So instead of a pyrochlore lattice with corner sharing tetrahedra, we now have corner sharing octahedra. And as you can see here, we can again just sum over these octahedra, square everything, and by construction we will have a spin, an ice rule constraint or a Coulomb liquid, which it characterizes. So, but you don't have to stop at that point. You can also consider further neighbor octahedra. So these blue sides belong to what is in this construction called the next nearest neighbor octahedra, and then these cyan colored sides, they are the further neighbors. And you add all these by parameters alpha and beta, and that allows you a nice rich phase diagram along which you can try to find for an emergent gauge law, emergent gauge field. And in this case only, it is not, as in the previous case, a rank 1 gauge field, but it's actually a rank 2 tensor, which Owen Benton was looking for. So the implication of such a rank 2 gauge field is actually, as Johannes mentioned in his talk yesterday, that not only you have conserved charge, but you will also have a conserved dipole moment, which basically comes from the second derivative that you take here. And if you have excitations which conserve the dipole moment, then it means that they will be immobile, so they cannot move without changing the dipole moment. However, if you take two of these excitations together, they are again conserving the dipole moment, and they can move. And such particles are called fractons, and they are very, very interesting for many for applications like topological quantum computing, because they have these very rich topological physics that I cannot go into detail here. So how do you construct these kinds of higher rank spin liquids in practice? As Owen pointed out, you can, first you characterize this phase diagram in terms of topological properties. So let's not go into detail what exactly these topological winding numbers here are, but essentially if you start in the blue phase and you move toward, along this red arrow to the phase boundary, an interesting thing occurs. So here I've plotted the classical structure factor in the large N approximation. So in this case, large N means just that the number of spin component goes to infinity. And if we start here at the left, you see a normal kind of Coulomb liquid which has just these twofold pinch points. But as you go along this line, you see that they start getting closer and closer together, and ultimately they merge in a single multifold pinch point. And this multifold pinch point is exactly what characterizes this higher rank gauge theory. So now, again, the natural question is to ask, okay, what happens if we include quantum fluctuations in such a system? And this is, of course, an easy question to ask and a much more difficult question to answer, because as you are probably very much familiar with, it's a problem which has an exponentially large Hilbert space. So exact diagonalization is limited to small clusters. It also violates the area law. So DMRG-based approaches are also very difficult. And okay, it's not surprising that this model is very strongly frustrated. So applying quantum Monte Carlo to this would be basically impossible. So what I will be doing instead is to use an FRG-based approach. Yesterday in another talk, you have been introduced to this pseudo-fermion FRG. And while I will not go into detail of what this is about, the spin operators are essentially replaced by fermions sitting on sides. And then the Hilbert space gets enlarged with some unphysical states that you somehow need to deal with. And typically you can only approximately deal with them by restricting yourself to 0 temperature. But once that is done, you can use functional renormalization group to solve this system approximately. Another approach that I want to take here is to express the spin operators in terms of Majoranas instead. These are not the Kita-F Majoranas that many of you are more familiar with, but these have the nice property. So there's only 3 Majoranas per spin, and these have the nice property that they do enlarge the Hilbert space, but only by including more and more physical copies of the original spins. So you can immediately work at finite temperatures without any problems and study the combined effect of thermal and quantum fluctuations with a lot more accuracy. Okay, so now let's consider this multifold pinch point. Here it's plotted in 3 dimensions, again, just for clarity. On this right-hand side, you see, again, a number of different methods. So this is what I've shown you before, the classical large N structure factor. And for thermal fluctuations included, the pinch point gets a bit broadened, but generally speaking, the spectral weight remains the same, and you can still see the generic shape of the pinch point. However, if we now include thermal and quantum fluctuations, we see something which is in contrast to what we've seen on the pyrochlore lattice, namely that not only do you get this broadening, which you might expect, but you also see that the spectral weight actually completely shifts away from the pinch point. So you could say that these quantum fluctuations seem to completely wash out these features and tear apart the multifold pinch point into its components. And you can see that if you lower temperature even further, so you remove thermal fluctuations, you will see that this is actually the effect of quantum fluctuations. So this ripping apart of the multifold pinch points continues even further at lower temperatures. So this was originally our question, and then we noticed also something peculiar, as I've pointed out, the points along the boundary of special interest. So another question that we ask ourselves is, okay, what happens if you approach several boundaries at the same time? So you are at these corners of the phase diagram where several boundaries meet. And what we found is actually there's a number of other interesting features that you can find in the structure factors, such as these quadratic type of pinch points. And recently they have been proposed in a paper by Hart to be connected to other kinds of fractonic theories called type 2 fractons. So for now, it remains to be seen if this is really a type 2 fractonic phase. This is something that we're still working on. However, according to this proposition, it's definitely an interesting gauge theory which arises there. And another observation that we've made is if we inspect this point here in the phase diagram, we find actually a line of pinch points. So a pinch line, as has been called by Benton in a recent paper for a much more complicated type of model, where you, if you take any cut along this red line here, you will always see a pinch point in the plane here. So let me also quickly talk about what the effects of quantum fluctuations are in these kinds of systems. So in this case, the plots on the bottom right don't show a zoom, but they just show basically a zoomed-in version of a cut along this black line here. So you can see the x direction remains the same, the y direction is now perpendicular. And unsurprisingly, for the classical case, we see a single pinch point along this arbitrary cut. Actually, you can also observe that at finite temperatures, this pinch point gets widened. So this is why you see this, this bright line across this pinch line. And again, if we include quantum fluctuations, we see that this pinch point everywhere along the line gets also torn apart by quantum effects. And in particular, also, again, there's some more shifting of spectral weight down to lower temperatures. And very similar is what we find for the case of these quadratic pinch points. So quadratic pinch points are basically pinch points where every single contour is parabolic. And maybe surprisingly, we still find that in the case of quantum fluctuations, these pinch points are not stable. And this is surprising because in this construction by Hart, it was pointed out that the combined effect of thermal and quantum fluctuations should be able to stabilize this kind of fractonic phase. So as of now, the only way to really check whether this classical construction actually produces the same gauge theory is to really do it by hand and expand this gauge field. So let me briefly summarize my main points. What I want you to take away is if you have an emergent gauge field, then typically that comes along with pinch points in the structure factor, and the shape of the pinch point indicates which kind of gauge field you have. I also want to point out that Benton's construction is very useful to study these higher rank spin liquids, but it can also be used to observe pinch lines and these quadratic pinch points, which was not known in the original publication. And as I mentioned, something to do is to really expand this gauge theory across, exactly at these points of interest and to find out whether they correspond one-to-one with this construction by Hart. So let me answer the initial question of this talk. Is the octoclaw model a higher rank quantum spin ice? And the answer is no, because as you can see, this pinch point feature basically disappears completely. But I don't think that means that this is not interesting to study in the quantum limit, because what you typically see for a generic kind of model is that the quantum structure factor doesn't differ all that much from the classical version. And here you can see that actually at low temperatures, there's a pretty significant effect of quantum fluctuations, which may indicate that there's some interesting quantum physics at play there. So as a result, I think for future studies, I highly encourage other people with good numerical methods to take a look at this model and to try to figure out what the ground state is of this kind of Hamiltonian. So with FRG, we were already able to verify that it's non-magnetic across the entire phase diagram, but whether it is maybe some kind of valence bond crystal or quantum spin liquid, or possibly even some more exotic kind of phase related to fractons, that remains to be seen. So, and with this now, finally, I also want to thank the people who've worked together with me on this project, my PhD advisor, Johannes Reuter, who unfortunately cannot be here today, and Yasir Iqbal, who was nice enough to invite me a few months ago to come visit him in Chennai at IIT Madras, where we started working on this project. And then I also want to thank Owen Benton and Roderick Mössner, who were nice enough to discuss some of our questions on this work together. And finally, I also want to thank you, the audience, for listening to this talk and hopefully ask some questions.
Okay, thanks. The talk is open for questions, comments. Yeah, Carlo.
Maybe I was not listening carefully for the, this octahedral edge sharing, corner sharing octahedra. You mentioned there is no spin ice. You looked at the Heisenberg model, or you can think about the Ising-like interactions, or?
So you mentioned that there is definitely a spin ice. So if you only take corner sharing octahedra, there's gonna be a spin ice. So essentially, wait, let me go back to this slide here. So essentially, what you are referring to is the case where alpha and beta equals 0, right?
Yes.
Yeah. Then you still have a spin ice, but you have a a normal rank 1 kind of spin ice that is very similar to what you have in the pyrochlore lattice. So if you're at this point in the phase diagram, you will basically just see a conventional two-fold pinch point.
Okay, thank you. Sorry.
Can you say something about low energy excitations?
Very good question. I'm afraid this is a very difficult question to answer because so in principle with PM-FRG, so if we study quantum and thermal effects, we actually have access to observables like the specific heat capacity. But I believe in order to, and I took a look at this, but in order to see something very interesting, I think we would have to go down to much lower temperatures. And currently this is a limitation of the method. And therefore I cannot make any claims about low energy excitations, unfortunately.
Any more questions by online participants? So if not, let's close the session by thanking all 3 speakers again.